This is A2Further maths, and it's our notes on induction with a few examples. So we're just going to talk you through, first of all, the general premise of it and what it is you have to do. For mathematical induction, so we're going to try and do proof here. We divide the proof into 3 steps. The first step, we want to prove that it's true for a small number. For example, we normally take a 0 or a 1. Step 2 is we assume it's true for n, and given it's true for n, we try and prove that it's true for n plus 1. For example, if we knew we were given it was true for 8, we're trying to prove it's true for 9, and so on, but we do it obviously for n. And step 3 then is if it's true for a small number, and if we know it's true for a given number, we know it's true for the next number, that's what step 2 says, then it must be true for all n. So step 3 then sort of summarizes that. So we prove it's true for a small number, and then we assume it's true for n, and try and prove that it's true for n plus 1. And by 1 and 2, if we know it's true for a small number, and if we can show, given it's true for n, it's true for n plus 1, then it must be true for all natural numbers. Let's take a look then at a couple of our examples. Prove by induction that 1 cubed plus 2 cubed plus all the way up to n cubed equals a quarter n squared upon n plus 1 whole squared. I hope you recognize that formula as the sum of all the cube numbers, and that's what we have here. So we're going to try and prove this using induction. Our first step, we need to prove that it's true for a small value of n. We're going to pick 1. So the left hand side of this formula just for the number 1 is 1 cubed, which obviously gives us 1. The right hand side, I sub the number 1 into this. So I'm going to get a quarter upon 1 squared plus 1, which is 2. 2 squared, that gives me a quarter, multiplied by 1, multiplied by 4, and that gives me 1. Therefore, it is indeed true for n equals 1, because the left hand side equals the right hand side. Step 2 then, we're going to assume that it's true for n equals k, and try and show then that it's true for n equals k plus 1. This is a new bit, it's quite tricky. We're going to assume that this statement here is true. You can just see it's the formula just above, and I've rearranged it. So anytime I've seen an n, I've exchanged it for a k. So we're assuming that this statement is true. 1 cubed plus 2 cubed plus all the way up to k cubed equals a quarter k squared upon k plus 1 all squared. The trick here then is to add the next term onto both sides. If I add the next term here, it's going to be k plus 1 all cubed. If I add the next term here onto the right hand side, it's going to be k plus 1 cubed as well. So that's what I have then written down here. If we take a look then at the right hand side, so I have a quarter k squared k plus 1 all squared plus k plus 1 cubed, and I'm going to try then and factorize that. So let's look at some common factors. Then I can take out, I'm going to take out a quarter out the front, and then I'm going to take a k plus 1 squared out of both terms. So a quarter k plus 1 squared, what do I multiply this by to get this? It's going to be k squared. What do I multiply this by to get this? It's going to be 4 upon k plus 1. So I have a quarter k plus 1 all squared, k squared plus 4 upon k plus 1. If I multiply out my small bracket here, I get k squared plus 4k plus 4. That factorizes to give me k plus 2 all squared. So I get a quarter k plus 1 squared upon k plus 2 squared. And I'm just going to rearrange this k plus 2 squared into a k plus 1 all squared. So why have I done that? I have a quarter k plus 1 all squared, k plus 1 all squared. This is just the above result with the k replaced by a k plus 1. So I hope you see that there. If we go back up to the top, this here was our formula. So it was a quarter k squared, k plus 1 all squared. But anytime I have a k here, I've exchanged it then for a k plus 1 down here. So that's proven it really. It's hard to get your head around that was what we've done. But we have added k plus 1. So what's the sum of all these terms here? It's just this here, which is the formula from above. Only anytime I have a k here, I've exchanged it then for a k plus 1. So what have I done? I've shown it's true for a small number. I did that above. I got 1 equals 1. And because it's true for k, then we've shown it's true for k plus 1. Therefore, it must be true for all n, which is a member of n. That's our first example. Let's take a look then at example 2. Prove the Mavris theorem by induction. This is the Mavris theorem here. You'll meet it a little bit later on. In fact, I think you maybe met it last year. Cos theta plus I sine theta to the power of n equals cos n theta plus I sine n theta. We're going to try and prove this using induction. Same plan as before. We show it's true then for a small number. So we're going to try the number 1. Exchange my n for a 1 here. I just get cos theta plus I sine theta. Exchange my n for a 1. I get cos theta plus I sine theta. A nice easy one then. It's true for the number 1. Next step, we assume it's true for k. So I just exchange all my n's here for k's, and we assume that this statement is true. Next, but slightly different than example 1, we're going to consider this. So what's this going to be? This is going to be cos theta plus I sine theta to the power of k plus 1. That's the same as cos theta plus I sine theta to the power of a k multiplied by cos theta plus I sine theta. So if you think about that, that's just their wee power of 1. So if you multiply those two things, because they're the same, you add the two powers, so that would be your k plus 1 down there. Multiplying out your brackets, the k comes down into there. We've shown that's true from above. And multiplying out your brackets, you get this big palaver of a thing. So cos theta plus I cos k theta sine theta plus I sine k theta cos theta plus I squared sine theta sine k theta. And we're going to take the real bits and the imaginary bits then of that. That's a real bit there, and because it's I squared, that's going to change into a minus 1. So this term here has gone to here. We get cos theta minus sine theta plus I then upon these two terms here. From your compound angle formula then for your A2 maths that you've done in A2 regular maths, the trig part, this can be written as cos k theta plus I sine k theta plus theta. Taking the theta out here, you get cos k plus 1 theta plus I sine k plus 1 theta. So what have we shown? We've shown that it's true for this. Given it's true for this, we've shown that this equals this. So it's also true then for k plus 1. All I've done here is, as you can see, this and this are equivalent to this and this, only with k plus 1 replacing the k. This is the above result replaced with k plus 1. That's what we've just said. Therefore, it's true. If it's true for k, then it must be true for k plus 1. So by step 1, we showed it's true for a small number, 1 in this case. And by step 2, then it must be true for all n. Final example then, and that's us done. Use the method of mathematical induction to prove that the expression 3 to the power of 2n plus 7 is divisible by 8 for all positive values of n. First step, similar. We're going to let n equals 1. 3 to the power of 2 times 1, so 3 to the power of 2 is 9, plus 7 is 16. 16 is famously divisible by 8, so it's true then for n equals 1. For the next step, we're going to let f of k equal 3 to the 2k plus 7. That's a mistake there actually. That should be the plus 7 written down there because the 7 isn't part of the power. If we've let that be that, then f of k plus 1 is going to be this, only a k exchange for a k plus 1. I hope you see then where I get that from. And we end up then with that. If we subtract these two, I guess this is the trick to this one. We're going to get f to the k plus 1, take away f to the k. The 7s there are going to disappear. I hope you can see what happens there. And we end up with 3 to the 2k plus 2, so that's just that bracket multiplied out, take away 3 to the power of 2k. Wee bit of a move here. This is the same as, so over here I've sort of explained where that's come from. 3 to the power of 2k plus 2 is the same as 3 to the 2k multiplied by 3 to the 2. Obviously if we were to do this in kind of year 10 indices, you add the two powers, so that's where they've ended up there. And 3 squared then is just 9, so this is the same just as this, because of this wee thing over here. Take away 3 to the 2k. You have 9, 3 to the 2k's here, take away 1, 3 to the 2k, so we just end up then with 8, 3 to the 2k's. K, as with n, are just going to be whole numbers, so no matter what number you put into this thing in the bracket gives you a whole number. If you multiply a whole number by 8, then it's going to be divisible by 8. That's what it says here. As 3 to the 2k is a whole number, then 8 multiplied by 3 to the 2k must divide by 8. Hence, f to the k plus 1 equals f of k plus 8 3 to the 2k. This is quite hard to get your head around, but this here we know we are given, it's given, you know, is assuming it's true. We're assuming this is divisible by 8. And if you add a multiple of 8 and you end up with this, then this must also be divisible by 8. If we have something like that we know divides by 8, for example, let's pick 40. And we add on another multiple of 8. So we add 24, which we know divides by 8. That's going to give us 64. Because 40 divides by 8 and 24 divides by 8, then 64 has to divide by 8. And that's pretty much what we're showing here. So f of k plus 1 is then divisible by 8. i.e. if f of k is divisible by 8, then so is f of k plus 1. So we're pretty much there. By 1 and 2 above. So by 1 was shown as true for a small number. And 2 is, assuming it's true for k, we've shown it's true for k plus 1. Then 3 to the power of 2n plus 7 must be divisible by 8 for all natural numbers.